Hello, I'm back again to talk about more about Flux. Um, Firstly, just a little review. We just finished the last two videos talking about circulation and flux. I would like to give a brief overview of the difference between the two. So, the one that I have written here on the left is the flux, and the one I have written here on the right is the circulation. And the only difference is that the vector field in flux is dotted with the normal vector. In the circulation, we dot the vector field with the unit tangent vector. Beyond there, they're practically identical. Of course, that dot product makes a lot of difference because n and t are at 90 degrees to each other. So you could say that actually when you have perfect flux, you have no circulation. When you have no circulation, you have perfect flux, so on and so forth. So, one thing that we've learned so far is that for almost everything that we do in vector calculus, we try to convert it to time. We try to figure out a way to integrate with respect to time or derive with respect to time. Because so far the lines that we've used, the parameterized curves that are vector curves, we've parameterized them in terms of time. So it's really useful if we already know the time value, or if we already know the parameterization of r in terms of time, that we kind of cater everything else to that. Now with circulation, it wasn't too bad. What we did here was we defined the dr, the absolute or the magnitude of dr is equal to ds. That's the only difference between dr and ds. They both have the same magnitude, but dr has a direction where ds does not. dr's direction is always in the tangent direction, so writing f dot t ds is equivalent to writing f dot dr. Now, once we get to this point, we can recall that the change in position, or dr dt, with respect to time, is equal to velocity. So we could rearrange this and say that dr is equal to v dt, and then we can do a simple substitution here for our circulation formula. And what we end up with is f dot v dt is equal to circulation. So that's, a three-step process to find circulation in a way to where we can integrate it with respect to time and not have to worry about changing our parameterized formula. Alright, so let's look at the flux, which is a lot more convoluted, but I figure it's important to see why we use the methods we do. So the key to this trick is we're going to go ahead and say, right off the bat, we're going to say, okay, the unit tangent vector is defined as velocity divided by the magnitude of velocity, which we can write further as v would be the change in the x component with respect to time and the change in the y component with respect to time. If there was a z component, we could do that as well. And then we will always divide by the magnitude of velocity, which is going to, well, it's going to be the Pythagorean identity of this. So in other words, dx dt squared plus dy dt squared. Alright, so now that we're at this point, we're going to ask a question. What is the relation between the unit tangent vector and the unit normal vector? The answer to that is that they're always 90 degrees separated. So imagine if we have here, let's say that this is our unit tangent vector t, and it will have a width of dx dt and a height of dy dt. Alright, so in other words, we've made a right triangle yet again, and this leg is dx dt, this leg is dy dt. This is our unit tangent vector. Well, our unit normal vector is is always at a 90-degree angle. And one thing that you may notice is that, and actually you can prove this to yourself, if you have an ordered pair on a graph and you want to find another ordered pair of the same length that's perpendicular, you actually flip. So in other words, you will flip. So let me draw it this way. Now this length for the unit normal vector, that actually becomes dx dt, but now it's in the negative direction. And this length right here is now dy dt, still in the positive direction. So in other words, we've gone 90 degrees from the unit tangent to the unit normal. And to do that, we flip. So in other words, we have now dy dt, dx dt. And if we look down here, the x actually changed sign, going from there to there. So we'll write it like that. Divided by, now it's actually going to be the magnitude of this. However, you'll notice that if dy dx gets squared, or I'm sorry, dy dt gets squared, dx dt gets squared, it doesn't matter if it was negative. So it's still the same denominator here. Alright, so now that we have that settled, this is equal to, this is a substitution for the unit normal vector. And another thing to realize here is that this whole expression here is just like we have it written up here. It's just the magnitude of v. So I'm going to go ahead and write it that way. That n is equal to dy dt, comma, negative dx dt divided by the magnitude of velocity. Alright, now let's look at this part of the formula, the ds. How can we write ds? Well, we know that ds dt is the absolute value of velocity. I'm sorry, ds dt is the absolute value of velocity because ds is directionless. We can rearrange this to show that ds equals the magnitude of v times dt. So we can substitute this into here, and when we substitute this and that into our flux integral, we'll find that we get f dot dy dt, comma, negative dx dt divided by the magnitude of v times the magnitude of v dt. So the magnitudes of v cancel out. The next step to this derivation is to assign the force, the vector field. We're going to say that it has some f of x and f of y component, and we're going to call those m and n, as they are in most textbooks. Alright, so now that we do that, we can actually dot. We can do the dot product now. Let me make some room up here. Alright, so I'll write it again. We have now f, which we've written in terms of m, which is a function of x and y, could be a function of x and y, times n, which is a function of x and y, dotted with dy dt, comma, negative dx dt, which is our normal direction, and then all integrated by dt. So let's go ahead and distribute here, and we'll find that m times dy dt, these two plus those two multiplied, which is minus n dx dt, dt is actually now, this is our flux integral. And this is one of the ways you may see it. You'll notice that the dt's can cancel, leaving you with m dy minus n dx, and it's written that way in books. But it's important that we keep it in this form for when we actually want to work with time. So in other words, we can now take our function r, which is parameterized in terms of x of t and y of t. now take dx dt and dy dt, multiply them by the force components in the x and y direction, and then integrate from our boundaries from across time. So now we've converted this into a form where we can use time just like we wanted to. And I hope this was helpful, and I'll see you next video.